Good morning, dear students. Today we discuss the second electron displacement effect, what is called resonance or mesomeric effect, abbreviated as R effect or M effect. Mesomeric effect, mesomerism is the former name and the modern name is resonance effect. Okay. The concept of resonance might be familiar to you. It is a phenomena by virtue of which a molecule is represented by more than one Lewis structure. In such case, we draw various resonance structures or contributing structures, and we said that the actual molecule is a resonance hybrid, which is an intermediate structure of various contributing structures. There are some wrong notions regarding resonance. It is that the actual molecule is one and only. It is our inability to represent it by formal structures. So we draw all possible structures, that's called resonance structures or canonical forms, and the actual molecule is thought to be an intermediate structure or what is called resonance hybrid. So we will be drawing various contributing structures in resonance. Another point is that resonance takes place in a molecule containing pi bonds, unsaturated molecules. It is a permanent delocalization of pi electrons, and it is predominant in conjugated system. What is a conjugated system? A molecule containing alternate single and double bonds, or sigma and pi bonds, or also it can be that's pi-pi interaction, or it can be also n-pi interaction. What is n? N indicate non-bonding or lone pairs, non-bonding electrons. So lone pairs can also get conjugated with a pi bond and take part in resonance. We will go to examples now, starting with butadiene, buta-1,3-diene, CH2 double bond, CH, single bond CH, double bond CH2. This is a conjugated system, alternate single and double bond, which is the right position for resonance to occur. We make use of the curved arrows for showing the movement of electron. What happens here? The pi bond, is weak. Pi electrons are loosely held. That's why they get delocalized, right? So the pi bond gets shifted to the very next place. Then the valency get disrupted here. It becomes 5. So naturally this pi bond will move to this atom, get localized on carbon. We make use of double-headed arrow to show resonance structures. What is the next structure coming? It becomes CH2. This becomes single bond. This becomes double, CH double bond, CH, and this again becomes single bond and CH2. Is it over? No. What is left out? We should put charges because there is charge separation here. See, this electron belongs to this carbon. When bond shifts, this carbon is losing this electron, so this carbon get a positive charge. And here, when this bond shifts fully to this carbon, it is getting this electron extra, so there will be a minus charge here, and we represent generally this as a lone pair. Remember, whenever there is a negative charge, there is a lone pair, even otherwise not mentioned. In some books, you won't see lone pair shown, only negative charge. That is enough. Whenever there is a negative charge, remember there is a lone pair, even if not explicitly shown. Okay. So these are the two structures. See, another notion regarding resonance is that it is not that there are two different forms of butadiene. It is not so. Like this is one structure at one point of time and it changes into other. It is shuttling. Interconversion of the two structures, like in equilibrium. No, it is not so. Remember, these are only hypothetical structures. Resonance structures or contributing structures are only hypothetical, and there is only one real structure which we are unable to represent in single structure, so we draw all possible structures. Right? So what is the actual molecule? Something in between. We move to the next example. It's more familiar to you. That is benzene. Benzene is a highly conjugated system with alternate single and double bonds. We will move the pi bond to the next place. Naturally, this will come here and this will come here. You have two equivalent resonance structures for benzene, right? What is also known as kecule structures. In the heart of the scientist who discovered this ring structure of benzene. These are the two major contributing structures of benzene, looking alike. The equivalent structure can be represented something like this. That is, what is happening here? The pi electrons are, it continues. This move to this, and it is a pi electron ring current. So we have to show is a broken line in strict terms. So the pi electrons get delocalized. It moves in a circular fashion, a pi electron ring. So what happens due to resonance? What is the consequence? The bonds get partial double bond character. Here it is a double bond, this is a single bond. But since it is moving, the pi electrons are moving, all bonds get a partial double bond character. Right? This one in quickly or in simple terms we just draw a full line. Strictly it is to be drawn broken line because it's only a partial double bond. Actually resonance leads to stability. You might have learned that. Resonance leads to stabilization. Benzene is highly stabilized by resonance, which is indicated by what is called resonance energy, resonance stabilization energy. Why resonance leads to stability? The logical part is that when electron gets delocalized, it is held by or it is under the attraction of many nuclei. See, if electron is localized, the pi electrons here is held by these two carbons. When the electron is moving around, it is held by all the 6 carbons. So the molecule get better attraction there. Okay, coming to the next example. Acetate ion. In the last class we have discussed this acidity of acetic acid, where we discussed about the resonance stabilization of the conjugate base or acetate ion. Right? This is acetate ion. Here there is a negative charge, you know that. Here this double bond, single bond and a lone pair. So this is an n-pi interaction. So this will shift here, and consequently pi electron move to oxygen. We can draw the next resonance structure as CH3, C double bond. Oh, this become double bond and this become single bond. And here 2 lone pair and here 3 lone pair with a negative charge. These two are equivalent structures. The resonance hybrid can be shown as CH3, CO, and both bonds get partial double bond character due to this delocalization, and negative charge get it moves moves to both oxygens, right? Okay, so this is another example. Then next example, see, this is another case. We are taking allyl carbocation. See, carbocations also show this resonance. Carbocation we will be discussing later. What is allyl group? CH2 double bond CH, single bond CH2. This group is called allyl. Just we said vinyl. This is called vinyl group. CH2 double bond CH. This is called allyl. And here there is a positive charge. This is a carbocation, right? So this is a double bond, pi bond is here, single bond, and this carbon, that is the carbocation, carbon carrying positive charge, it is in sp2 hybridization and it has a p orbital in perpendicular position, so it can overlap laterally, so resonance is possible. We show it like this, shift to this position, pi bond shift to this position, so we get CH2, this becomes single bond, CH, and this become double bond. What else? Positive charge, plus is here, there should be a plus here, and that appear here, because when this shift, this carbon losing this electron. Remember, whenever you draw structures and equations, etc., electrical balance is an important guide. There should be electrical balance. If there is no charge on left side and the other side also, it should be, total charge should be 0. Here there is a plus charge, there should be a plus charge on this side also. Okay. And so the point is, there is resonance taking place in carbocation also. There is another example that is a similar one, but it is free radical, allyl radical. Here also there is conjugation. CH2 double bond CH, single bond CH2 and dot. What is this dot? Unpaired electron. That is free radical. Here the difference is we use half-headed arrow or fish hook because one electron is already here, so we need to shift only one electron, right? So that you get, this will become CH2, this bond breaks, so it becomes single bond CH, and when one electron comes here, using this electron, it forms a double bond CH2. What else? This electron is left out, so that is to be shown here, right? This is allyl radical, which is stabilized by resonance. See, resonance has a lot of applications in different properties of the molecule. You will come across all these in different modules of organic chemistry. Okay, now, so we learned what is resonance. Next is the effect due to resonance, that is similar to inductive effect. Different functional groups can exhibit or exert either electron withdrawing or electron donating effect due to resonance, right? So there can be two types of functional groups, minus R groups and plus R. What is minus R? Electron withdrawing resonance effect, and plus R, electron donating resonance effects. So minus R or minus M groups are those groups which withdraw electrons towards them, withdraw the pi electrons towards them, and they acquire negative polarity. Whereas plus R or plus M effect is electron donating resonance effect, means certain functional groups, they will have lone pairs and they donate their electrons away from them and they develop a positive polarity. We will discuss now. Which are the important minus R groups? Let us know. Groups like carbonyl group, like in aldehyde and ketone, nitro group, then as carboxylic acid group, COOH, CN, cyanide or nitrile group, SO3H, etc. What is the common feature of these minus R groups? All of them contain multiple bonds, double or triple bond, and also it is connected to an electronegative atom so that they can withdraw electrons. And plus R groups are electron donating resonance groups are OH, OR, NH2, NHR, NR2, and also halogen. What is the common feature of these groups? All of them possess at least one lone pair. They have lone pair, right? So these are the two types of resonance groups. We can now take example to explain these two types of resonance effects. So resonance are of two types, that is minus R or minus M effect, electron withdrawing resonance effect, an electron donating resonance effect. We will put examples. Putting example for minus R effect, let us take, for example, this one, CH2 double bond CH single bond C triple bond N. What is this? Vinyl cyanide, right? Propiononitrile, that is the IUPAC's name. This group CN is minus R group. Nitrogen is more electronegative, so naturally this pi bond will be attracted towards nitrogen. Carbon develop a positive polarity, so that will be pulling this pi bond towards this place. So pi electrons moves. We get the next resonance structure. CH2 single bond CH double bond C double bond N, and what more? Charge separation comes. This carbon loses this electron and it becomes plus, and this nitrogen get the lone pair or negative charge. Okay, this is the resonance structures of this nitrile. So such groups are withdrawing electrons and develop negative polarity. Withdrawing electron towards them. This is minus R minus M effect. Coming to the next one, that is plus R effect. Plus R effect or plus M effect, that is electron donating resonance effect. Certain groups donate electrons away from them. Let us take an example. This one, CH2 double bond CHCl. What is this? Vinyl chloride. You know, chlorine has lone pair. So this is a conjugation. Pi bond or double bond, single bond and a lone pair is the right position for delocalization. What happens here? This pi electron, this lone pair will come to this place, so that the pi bond should move to this carbon. We get the next resonance structure. CH2 single bond CH double bond CH2. What about the charges? Carbon develops, this is Cl. This chlorine develops a positive charge, and this CH2 develops a negative charge and lone pair. Due to this, what happens, the carbon chlorine bond here is becoming double bond, or it becomes stronger. So that is why we say that vinyl halides resist SN reaction. You might be learning SN reaction elsewhere, nucleophilic substitution reaction, which is a very common reaction for alkyl halides, but vinyl halides resist the reaction because of this resonance effect. Okay. Now, finally, application. What are the applications of resonance? Resonance has immense application, in various properties of the molecule. Here we discuss only one. That is regarding the electrophilic substitution reactions of benzene. Benzene is having delocalized pi electron cloud. So electrophiles easily attack benzene, and it can substitute one of the hydrogen on benzene, forming various products. There are reactions like nitration, sulfonation, Fidelkraft alkylation, acylation, halogenation, etc., which are all electrophilic substitution reaction. The point here is the reactivity of benzene towards this electrophilic substitution reaction is highly influenced by the substituents present on benzene ring. That means if benzene is carrying one functional group like nitro group, OH, NH2, etc., then the reactivity of that benzene ring is influenced. Basically, there are two types of such effect. One is deactivating groups. Certain functional groups deactivate benzene ring towards electrophilic substitution reactions. That is nothing but the minus R groups. Electron withdrawing resonance groups like these groups, what they do, they will withdraw electrons away from benzene ring, so that what happens to the electron density of the ring, it decreases. Then electrophile will find it difficult to attack, reactivity decreases. We can take an example. it's very important in practicing drawing resonance structures. That is what is all important in this discussion. How well you can draw resonance structures. Let us take nitrobenzene. See that nitro group is a minus R group, and see when it is connected to benzene ring, it is conjugated by double bond, single bond, double bond, and this is oxygen. So what happens? Oxygen will pull electron towards it. Naturally, this pi bond will come out to this place. We get the next structure, right? It becomes N single bond O, and this is a coordinate bond, and then these two bonds are intact. This carbon loses one electron and get positive charge, and oxygen get negative charge. I am avoiding lone pair. There is lone pair, of course. Other lone pairs are also there. I am avoiding that. Now what happens? It continues one at a time. We shift one bond at a time. In the next structure, this pi bond move to this place. It is like what happened in the carbocation. It can move to this place. Okay. So, one is missing here. It is double bond, right? This become double bond. So, it is now that these two bonds and negative positive charge is now here, and now this will move. You get the next structure. Okay, it is now like this. Positive charge is now here. What is happening? The electrons are delocalized and positive charge also get delocalized in turn, and finally it come back. So it is completed. Now it will come back. Electron is withdrawn first by oxygen. Now it is coming back. So the pi bond will come back to this place, and you get the final structure. It is now single bond. This is now double bond, and it is like this. So you get 5 structures. This is very, very important, very noticeable. There will be 5 structures whenever you draw resonance structures for benzene, substituted benzene. The first and the last, you may think they are same. No, it's not same. You can check the position of the double bond. It is interchanged. So these are the Kekulé isostructures of this nitrobenzene. So these 5 resonance structures represent the structure of nitrobenzene. Now, what is the point here? Why these are called deactivating groups? Because these groups are withdrawing pi electrons. And ring get positive charge. Positive charge indicate electron deficiency. So when nitrobenzene electrophile will find it difficult to attack benzene, reactivity decreases, right? Whereas on the other hand, the plus R groups, electron donating resonance groups, they will activate the ring. Activating groups, that is plus R groups. Why they are called activating? When these groups are connected to benzene, what happens? The lone pair on these function groups will flow into the ring by resonance, and the electron density of benzene ring increases. So the electrophile will find it easy to attack, reactivity increases. That's why they are called activating groups. Let us take an example. We have here this compound. What is this? Aniline, right? Aniline, nitrogen has a lone pair. Okay. This is also conjugation, double bond, single bond, and lone pair. So lone pair can now move, get delocalized into the ring. We can draw 5 structures here also. Okay. This become double bond, and here positive charge, and what else? This carbon get negative charge, and there is a lone pair. I am not showing lone pair, and it will continue. This lone pair will now move to this place, and this pi bond to this carbon. We get the third structure. It is now like this, and it continues. This is now shifted to this carbon, getting the 4th structure. Okay, and finally it is getting back. The lone pair get back to nitrogen in the final structure. It is again now back to single bond, and you get the fifth structure. Here also you have 5 structures. See what is, again repeat that you should spend time to practice drawing this picture. That's all important. So here in this case, these functional groups having lone pair will donate electrons to the ring through resonance, and electron density increases in the ring, that is vivid from the negative charge on the ring. So electrophile will easily attack benzene ring and reactivity increases. So this is application of resonance. We discuss it here. You will find various applications in other areas of organic chemistry. Okay, so we will discuss the next electron displacement effect in the next class. Till then,